Hi and welcome to my video series on anti-differentiation. You'll learn more about the process, but you'll also learn about the naming conventions as we go forward. But really, right at the start of this topic, it's usually called anti-differentiation. You'll note here on my OneNote that I've got the learning goals for this topic. I've also got some success criteria. It doesn't look like much, but there's a lot to learn, but it's all fairly procedural. So you'll see there's a lot of exercises in the textbook that we use. And also you'll see some links here to videos that I've made on the Lightboard and also on my YouTube channel, so you can check those out if you want to. So anyway, without further ado, let's look at the first section of anti-differentiation. So as you can imagine, anti-differentiation is the opposite to differentiation. And that's why it's called anti-differentiation. It's also known as integration. So you'll see that integration in there as well. So most things can be anti-differentiated. Some things can't though, and some things can't be anti-differentiated until you're doing higher levels of maths. So you'll probably find that as you're doing anti-differentiation and differentiation, you're able to differentiate more functions than you're able to anti-differentiate. And that's fine. As long as you do the practice and you're aware of the function groups, you'll know what you can and can't do. So let's have a look at some basic examples. First of all, let's take 2x squared, y equals 2x squared, and let's get y equals 2x squared and derive it. And so if I derive y equals 2x squared, I get dy dx is equal to 4x. So you recall that when you derive, you bring the power down as a multiplier at the front and you decrease the power by 1. So just following this purple arrow, you see that that means in reverse, if dy dx equals 4x, then y must equal 2x squared. Now, for those of you more familiar with this topic, you'll know there's a couple of things missing here, but this is the basic premise. The basic idea of anti-differentiation is that we're backtracking to what would have been differentiated to get the original function. And in this case, it's 2x squared. So let's also consider some other derivatives and talk about the main thing that we actually are missing. So let's imagine we have y equals x cubed. If y equals x squared, hopefully you can see that dy dx is equal to 3x squared. And if y equals x cubed plus 6, hopefully you can see that dy dx is equal to 3x squared. Remember that plus 6, the constant just disappears. And if y equals x cubed minus 3, well, dy dx equals 3x squared. And I hope you can see where this is leading. If dy dx equals x cubed plus pi, well, dy dx just equals 3x squared, because in each case of that constant, it just disappears as part of the process of differentiation. So what this means as a corollary to that is if dy dx equals 3x squared, well then y is equal to x cubed, but there might actually be a constant there. That might be plus 6 or minus 3 or plus pi or any other number of things that exist in our real number system. So what we do instead is we introduce a constant of integration. So we integrate or we anti-differentiate, and when we do that, there may have originally been some constant there. In fact, it's easy to think of it as there was a constant there, it's just sometimes that constant is 0. And that way you're always remembering to put it on there. So let's have a look at that, the effect of that on Desmos. So here's my link from the OneNote. It just leads to this really simple thing here. But I want to show you, this is with the x cubed again, here's my x cubed graph. I want to show you what happens when we differentiate and why that constant of integration exists. So remember, when we differentiate x cubed, it's a rate of change function. So it's describing the gradient at any point. And that's really important to remember. So what I can do is I can add the rate of change function here. We could have a further play with that. But what I want to show you now is if I change the value of a, you remember that a is a vertical translation. So it shifts the graph up and down. So if I play this now, this animation, have a look at the graph moving up and down first of all. You can see it there, sliding up and down, disappearing momentarily. Now, tell me, or think about this, it's a video, you can't really tell me, what changes in terms of the gradient? And the answer to that is nothing. The gradient at a particular point, the steepness, is exactly the same because the graph's not changing. It's just moving up and down, but the actual steepness at that particular x value doesn't change. And so it's really important to recognize that differentiation with a constant produce the rate of change function irrespective of that constant. And so therefore when we integrate, it could be this x cubed graph that has a constant value of 0, or it could be this x cubed graph that has a constant value of 3.42. It could be a whole range of different things. So we just don't know what that constant is. Anyway, let's carry on. So remember, anti-differentiation is integration, and there is some notation associated with this. So we'll talk about this, but it's this kind of elongated S symbol. And so when we integrate dy dx with respect to x, the answer is y. Now that looks a bit confusing, but the easiest way to get your head around it is to do some questions and get used to that notation. Really, the bit that's mostly confusing here is that dy dx being in there. But you can see here that the dx's kind of cancel out. With the integral of dy equals y, it kind of makes sense. But this is what it's saying. So the next line down here, let's have a look at this one. This is saying, what is the integral of 3x squared with respect to x? And the answer is x cubed plus some constant that we don't know. And the next one down is saying, what is the integral of 4x with respect to x? And the answer is 2x squared plus some constant that we don't know. So that's what it's saying. Hopefully the only thing that's really maybe a bit of a struggle now is the idea of with respect to x. What does that even mean? And I'll talk about that a little bit later. I've got a good example set up that will help show you that. But the generalization, for polynomials at least, is this. If y equals axn, ax to the power of n, then dy dx equals an x to the power of n minus 1. We bring that power down, decrease the power by 1. And so therefore, the integral of ax to the power of n with respect to x is equal to ax to the power of n plus 1 over n plus 1 plus c. So if I was going from there to there, I increase the power by 1, and I have to divide through by the new power. It's the opposite to differentiating. In differentiation, we lower the power by 1 and we multiply by the old power. Now we increase the power by 1 and we divide through by the new power. So you can see that here. Here's our original function. The a has remained the same. We've increased the power by 1 and we divide it by n plus 1. And we have our constant of integration, that unknown constant. So here's some examples. And example D is going to give me an opportunity to talk about with respect to x in a little bit more detail. There's a couple of further rules that you should be aware of, and they're over here, and they're really simple. I know it looks complex, but they're really simple. So it's just basically saying if you're integrating two functions that are just added together, well, that's the same as integrating each function separately. If you're integrating two functions that are subtracted, or a difference between two functions, that's the same as the difference between the integral of the two functions. So you can separate these integrations. You don't have to make things more complex. And this last one is if you have a constant times a function, well, then the integral of this constant doesn't really change anything. You can bring it out the front if you want to, and it doesn't make any difference to the original function that you're integrating. That will become more important a little bit later on as well. So here's my answers. The integral of 2x cubed is equal to x to the power of 4. Remember, I increased that power by 1. The 2 is a constant, so it has no effect, over the new power 4 plus c. And of course, that is equal to a half, x to the power of 4 plus c. Always look for that extra opportunity to simplify, which might exist. The next one is the integral of 3x squared plus 6. And this is equal to x cubed. This x squared becomes x cubed. The 3 is still there, and we divide by 3, the new power, and the 3's cancel out, of course. And then 6 becomes 6x and plus c. So you ask yourself, what will have derived to give 6, and that is 6x. But you can do the whole stuff with x to the power of 0 if you want to, but that's the general rule. If you integrate a constant, you get 6x, or the constant times x. And so this simplifies down to be x cubed plus 6x plus c. And the next one, the integral of 3a plus 2 with respect to a. So you're starting to see this with respect to come through. And this gives we're integrating with respect to a, which means we get a becomes a squared. The 3 remains, and we divide by the new power, plus 2a, that's what we do with the constant, plus c. And we can't simplify that one, so I'm just going to leave it like that. And the last one is the integral of 2wx squared minus x with respect to x. So it's important to recognise here that we're deriving with respect to, or integrating with respect to x, so the w is treated like a constant. So it just sticks and hangs out with that 2. We're not integrating with respect to w. If that was the case, then the x would remain like a constant. That's where that with respect to x comes in. The good news is that you won't really have to deal with this much in math methods. Specialist maths, it might come up a bit, but really it's later on where you get into multivariate calculus that this becomes a bit more important. So for now, this becomes 2w, the constant stays the same, x cubed over 3 minus x squared over 2 plus c, and I can't simplify that, so I'm going to leave it as it is. And you can see there I've followed the rules, done everything that we've set up previously in this video. Well, thank you for listening. The second part of this exercise I'm going to go through in the next video, so maybe have a look at that, and then we'll continue to move forward in just little pieces. All the best.